Hello, this video is an introduction to bonding and how we model bonds. So I'm going to start by showing an animation. So let me just go into the animation for a moment.
Most atoms don't ride solo. Instead, they bond with other atoms. Now, bonds can form between atoms of the same element, or atoms of different elements. You've probably imagined bonding as a tug of war. If one atom is really strong, it can pull one or more electrons off another atom. Then you end up with one negatively charged ion and one positively charged ion. And the attraction between these opposite charges is called an ionic bond. This is the kind of sharing where you just give away your toy to someone else and then never get it back. Table salt, sodium chloride, is held together by ionic bonds. Every atom of sodium gives up one electron to every atom of chlorine. Ions are formed, and those ions arrange themselves in a 3D grid called a lattice, in which every sodium ion is bonded to 6 chloride ions, and every chloride ion is bonded to 6 sodium ions. The chlorine atoms never give the sodium atoms their electrons back. Now, these transactions aren't always so cut and dried. If one atom doesn't completely overwhelm the other, they can actually share each other's electrons. This is like a potluck, where you and a friend each bring a dish, and then both of you share both dishes. Each atom is attracted to the shared electrons in between them, and this attraction is called a covalent bond. The proteins and DNA in our bodies, for example, are held together largely by these covalent bonds. Some atoms can covalently bond with just one other atom, others with many more. The number of other atoms one atom can bond with depends on how its electrons are arranged. So, how are electrons arranged? Every atom of a pure, unbonded element is electrically neutral, because it contains the same number of protons in the nucleus as it does electrons around the nucleus. And not all of those electrons are available for bonding. Only the outermost electrons, the ones in orbitals furthest from the nucleus, the ones with the most energy, only those participate in bonding. By the way, this applies to ionic bonding too. Remember sodium chloride? Well, the electron that sodium loses is the one furthest from its nucleus, and the orbital that electron occupies when it goes over to chlorine is also the one furthest from its nucleus. But back to covalent bonding. Carbon has 4 electrons that are free to bond. Nitrogen has 3, oxygen 2. So carbon is likely to form 4 bonds, nitrogen 3 and oxygen 2. Hydrogen only has 1 electron, so it can only form 1 bond. In some special cases, atoms can form more bonds than you'd expect, but they better have a really good reason to do so, or things tend to fly apart. Groups of atoms that share electrons covalently with each other are called molecules. They can be small. For example, every molecule of oxygen gas is made up of just 2 oxygen atoms bonded to each other. Or they can be really, really big. Human chromosome 13 is just 2 molecules, but each one has over 37 billion atoms. And this neighborhood, this city of atoms, is held together by the humble chemical bond.
Okay, so this video kind of gives an overview of bonding, but we're gonna go slow, and we're gonna go into each type of bonding. So if you didn't get everything from the video, it's okay. The whole idea of the video is for you to get an overview. So a few things that I wanted you to have gotten from the video. One is that very few elements are found pure and unbonded. Okay, they're very, very rare. Elements are most stable when they are bonded to another element or to itself. And then the third thing is bonded atoms are called molecules or compounds. So those are the 3 things I wanted you to have taken away from the video. So why do atoms bond? Well, they bond to reach stability. And we have this rule, which does not apply to all atoms, but we're going to use to the atoms that it does apply. It's called the octet rule. And the octet rule says that atoms are most stable when their orbitals are full. So let me get my pen out. It is this. All right. So if you look over here, this is sodium. Okay. And if you look, this is the Bohr diagram for sodium. And if you look over here, there we go. The first orbital here has 2 electrons, and that's the largest amount that it can be in a first orbital. So the first orbital is full. The second orbital right here, it has 2, 4, 6, 8. The second orbital is also full. The third orbital is not full. It only has 1 electron. So sodium right now is not stable. Okay. Let's look at another example. Let's look at chlorine. So chlorine right now, the first orbital is full. It has 2 electrons. The second orbital is also full. It has 8 electrons. The third orbital right here is not full. It only has 2, 4, 6, 7. Okay, so it's not full. In order to be full, it needs to have 8. Okay, that's why it's called the octet rule. Okay. Okay, so then, in order for us to talk about bonding, we only need to worry about the outer electrons, and they're called valence electrons. So this is how it's done. It's pretty straightforward. Let me get my thing. So the way we look at it, we only are concerned about valence. There you go. Valence electrons. Okay, that's the only thing that we're concerned. For in the case of sodium, the valence, I'm just going to abbreviate valence electron. Valence electron. Why is this not showing? Okay. I don't know why this is not showing. I'm just going to use V for valence electron. For some reason, every time I put an E, it thinks I want something else. So I'm just going to put it here, valence electrons. So equal, in this case, equals 1. Okay, and then valence electrons here, we have 2, 4, 6, 7. The valence electrons here is going to equal 7. Okay, let's try this again. Valence electron equals 1, and then valence electrons equals 7. Okay, so 2, 4, 6, 7, and only 1. So because we are only concerning bonding valence electrons, we only need to worry about the outer electrons. Let me erase, and then let me get out of here, and then moving on. So now it's your turn. I would like for you to determine how many valence electrons is in oxygen. Okay, so hopefully you answer that question, and let's work on it together. Okay, so we have the first orbital is full, the second orbital is right here. Actually should be, yeah, second orbital. So we have 2, 4, 5, 6. So the number of valence electrons for oxygen is 6. Okay, let me erase. Alright, so now we're going to try to abbreviate this because we don't need to always show Bohr models when we're talking about bonding only. Okay, so the Lewis dot model is an abbreviation of Bohr model, and this is what you need to do. The first thing to create a Lewis dot is to write the symbol of the element, which in this case is sodium, Na, and then you only write the valence electron. In this case, you just put one dot. This is the Lewis dot model for sodium. The same thing with chlorine, so you do the symbol Cl, and then there are 7. So you do it like this: 1, 2. It's supposed to be dots. It's just not very good dots. 1, 2, 3, 4, 5, 6, and 7. Okay, let me clear this up and do a better job. For chlorine, I'll just do it this way: 1, 2, 3, 4, 5, 6, 7. So I just kind of rotate clockwise. The idea is that it has 4 sides: 1 side, 2 sides, 3 sides, 4 sides, and you put 1 around until you get the correct number. So that's the idea behind how you draw a Lewis dot model. Okay, so now again is your turn. Which model is the correct model for Lewis dot model for nitrogen? So take some time. There's A, B, C, and D. Go ahead and choose the correct one. Okay, so let's look which one is the correct one. A is not the correct one. A is a Bohr model, is not a Lewis dot model. So now I know that nitrogen has 5 valence electrons, right? So if I do the Bohr model, I ended up with nitrogen having 5 valence electrons. So therefore, it should be number B, or letter B. There is a way to find valence electrons just by looking at the periodic table. So if you have a periodic table in front of you, the first column, all of the elements in the first column will have 1 valence electron. All of the elements in the second column will have 2 valence electrons. We'll ignore those transitional metals. Then here begins 3, 4, 5, 6, 7, and 8. This column over here is called the noble gases. Everyone in this column, or every element in this column, has a full orbital. Therefore, they don't really bond. They're non-reactive because, again, they have full orbitals. They don't need to do anything to be stable. They're extremely stable already. So noble gases do not react. Okay, so there are cases where, and this is not every case, but there are cases where in order for an element to become stable, it needs to either give its electrons or it needs to take in its electrons. So the way we know what gives and what takes is by looking at the periodic table at metals, nonmetals, and metalloids. Metals give away their electrons. Nonmetals take electrons, and metalloids goes both ways. I usually don't ask you guys about metalloids. Okay, I focus on nonmetals and metals. So, a quick checking for understanding. Sometimes elements take, this is misspelled, take in or give away electrons in order to reach stability. Based on the previous explanation, do you predict the magnesium, Mg, will give or take in electrons? Okay, so take some time, look at the periodic table, look where magnesium is located, and then determine whether magnesium will give away its electrons or will take electrons. It's easy. We just look at the periodic table. Magnesium is right here. Magnesium is a metal, therefore it's going to give away its electrons. Okay. So what happens when elements gain or lose electrons? Well, if they lose their electrons, they'll have an overall positive charge and it'll be called a cation. If they gain electrons, they will have an overall negative charge and it will be called an anion. Let me explain. I think I explained that before, but I'll explain it again. So if you have a neutral element, I'm just going to pick up this one, lithium, because it's easy. If I have a neutral element, and in order for something to be neutral, it has the same number of protons as electrons. Okay, so let's make this into a cation, meaning lose an electron. So if, oh, it erases the whole thing, huh? Alright, so let me do this again. Okay. So this is a neutral element, but let's say it's going to lose this electron. So this is how it's going to end up being. Again, the protons will never change. Okay. So this cancels with this cancels with this, and the overall charge will be positive. Okay. Let's look at anions. Again, let's use the same example. Okay. The number of protons is the same as the number of electrons in here. This is neutral. However, if it is an anion, it's going to gain electrons. So let's add an electron to this. Go, this cancels with this cancels with this cancels with this, and the overall charge will be negative. So that's where the negative and the positive comes from. Alright, so looking at the periodic table, we can predict whether something will gain or lose electrons, and also we can predict how many electrons will gain or lose. So again, like I said, metals, they lose electrons, and if they lose electrons, they all have a positive charge, right? Those are all the metals. They'll have a positive charge. Non-metals, I said, gain electrons, so they'll have a negative charge. Okay? So that's why you have a negative charge in here. So this is how you can tell. So this family has one valence electron, and in order to be stable, it needs to lose one electron. So you have a +1 charge. This family has two valence electrons. In order to have a full orbital, it's going to give away its 2 electrons. This family has 3 valence electrons. In order to have a full orbital, it's going to give away its 3 electrons. Group 4 can go either way, and group 4 usually don't have that behavior. But let's go to group 5. Now group 5 has 5 valence electrons. So it can either lose 5 electrons or it can gain 3. It is easier to gain 3. So it's going to gain 3 electrons. This family has 6 valence electrons. Again, it can either lose 6 valence electrons or it can gain 2. It's easier to gain 2, so it's going to have a -2 charge. In group 7 is only missing 1 electron in order to be stable, so it's going to gain 1 electron. Okay, so let's look at that. So you can use this table to help you figure out what charge an element will have. Let's see. Find the ion form. So I'm going to show you how to do that. So this is magnesium. Magnesium, let me write it down. Magnesium, if you look at the periodic table, it looks like this. 1 dot here, 1 dot here. It has 2 valence electrons. Okay, so you can either gain 6 or you can lose 2. It will lose 2. So magnesium, the ion form of magnesium is going to be without those 2 electrons, and it's going to have a +2 charge. Or sometimes we write 2+. Okay, the same thing. This is the correct way of writing. We're saying that there's 2 protons without an electron. But this is the cation, and it's a cation, right? Because it's positive. Cation. Okay, I'm going to erase and then move on to the next one. Okay, fluorine. Take some time, pause the video and try to do fluorine. Alright, so fluorine, if you look at where it is in the periodic table, it has 1, 2, 3, 4, 5, 6, 7. It has 7 valence electrons. You're just missing 1 electron here. So fluorine is going to gain an electron. So its ion form is going to have -1, or sometimes we write 1 negative. Again, this is the correct form. And it is an anion. Anion. Okay. Okay, now it's your turn. Go ahead and find out the correct form of potassium ion. Okay, so what is the ion form for potassium? Okay, hopefully you got it right. So this is the correct form for potassium. I have to write it down. This is the correct form for potassium. Okay, and it is a cation. Okay, another one for you. Go ahead and do the ion form for sulfur. Okay, this is the ion form for sulfur. By the way, this is a 2. Okay, some takeaway points. Pure elements are very rare. Okay, most elements are combined with something else. Valence electrons are responsible for bonding. Valence electrons are the outer electrons in a Bohr diagram. We use Lewis dot model to show valence electrons, and it's just the symbol and the number of valence electrons. Atoms bond to reach 4 orbitals. In most cases, it's 8 electrons is a 4 orbital, except for the first orbital, which only has 2. Sometimes, not all times, and I'm going to show you both ways, sometimes atoms become ions in order to reach stability. Metals lose electrons, and we call them cations, and they have a positive charge. Nonmetals gain electrons, they're called anions, and they have a negative charge. And I think that's about it. Let me know if you have any questions.